Hello everybody, welcome again to this beginner's screencast on MPS. Well, this time I'd like to continue on what we've done in the previous two episodes and focus on constraints, touch on the type system topic a little bit, and enhance our knowledge of the generator a bit. And to do that, we'll continue in the same code example we used over the past two episodes, our constant DSL, a DSL for defining constants, but this time we'll evolve it a little bit further. So, what we can do at the moment is that we can define constants with a name and with values, and values can be expressions, but we explicitly restricted them to be only scalar values. Today I'd like to enhance constant definition so that we can do stuff like here in Java, where you can, when you define a constant, you can refer to the other constants. So like you can say, well, the default should be 20 plus the, well, maximum, for example. And you can't refer to the constants below, so you can't make forward references, so you can't go to normal rate because now it gets underlined telling you that this is not right. So we want to achieve the same capabilities in MPS. Let's do it. So to allow references, so we might want to refer from minimum to maximum. At the moment we can't do that. Code completion won't allow us to refer to maximum. It's not visible at all. Plus, we have to remove the restriction that we have at the moment. So currently, constants explicitly are restricted to only scalar values in the initializer. So we'll remove that restriction so that we can make more complex initializers. So that's the first thing we have to do. And now we have to declare references. So to allow minimum constant, the initializer, to refer to maximum, we have to create references that would go across the AST and point to the definition of the maximum constant. So we need a new structure, we need a new structure element, a new concept. We'll call it constant reference. Constant reference. It will extend an expression, so we can make it part of the initializer, which is also an expression. So now we have the reference. Now we need this reference to point to the definition. So the reference, so our reference has to reference the constant definition. So that's the concept is called constant. We give it a name, original. And it's exactly 1. So this reference points to exactly 1 constant definition. Now we need an editor. Well, the editor will be pretty simple. We just say we want the original, and from the original we want to show only the name. So this is the editor. I guess we should give it a try. So I'll rebuild the language. And now we can try. So 0 plus maximum. Here we go. Code completion knows about maximum. We can add maximum. We can go Command B to definition of maximum. Well, we can search for usages, so it will highlight all places where maximum is being referred. Okay, well, so we can do these references. However, there are problems. There are problems in types, for example. So we have here where we define flag, which is we assign boolean true. Now we can go minus whatever, minus name, and it's all happy. It doesn't complain about this, which I don't think is right. True minus a string. What type is it? Is it compatible? Can you do that? I guess we should introduce types to our constants. So we should declare that a reference has a type of the constant it's referring to, and the constant also has to have some sort of type. So let's do that now. So first we go to the constant reference, and we just say the constant reference should have the type of the constant it refers to. So now we go to the type system and we create a new inference rule for the constant reference. These rules will be pretty simple. We're just starting with type system, so we're not going to get any deep into what the type system can do. So just scratching the surface, the type of the constant reference should be equal to the type of the original, so the referee, the definition of the constant. So now we only propagate the type from the constant to references to the constant. However, for the constant itself, we also need a rule that would say what type the constant has. So the constant, well, the type of the constant in our example should be the type of the initializer of the constant. How about that? So I'll try to rebuild. Okay, and here we have a problem, a type system error, operation not allowed. It's not applicable to these operands, so you can't do minus on a boolean and a string. So now we have a type system taking care of correct types being used. Well, good. So now we have the type system. Now look at this. What happens if I define another set of constants? So let's call it your constants as opposed to my constants, so we distinguish them. Well, here we can have also maximum, which can be what, 50 for example, and we can have something very noticeable, so foo, that we won't miss that one, and can be a string of foo. So that's our so we should call your constants. Good. So now we have two set of constants, and we can, however, cross-reference. So you see, we see constants from both, which in my case I would like to disallow. So I don't want to refer from your constants to my constants. So you see this flag here. If I go Command B to definition, I jump to my constant. So this is the one I refer to. So I cross-refer from this set of constants to that set of constants, and I want to disallow that. Let's do that. Well, clearly we need to set scopes on the references. We have to restrict the references on where they can point to. So now we go to the reference. So this is the constant reference, and we add constraints. And in our case, we go to referent constraints. So the guy this reference can point to So we say which link. So this reference is only one link called original. So original will be restricted, and the search scope, the scope in which we'll be searching for the constants, is only within the scope of the current root, which is the set of constants concept. So we are supposed, from this function, we are supposed to return a list of allowed constants that we can point to. So what we do, we take the enclosing node of the reference, so the reference that we are trying to build the search scope for. It's encapsulated inside something. For example, here the flag is now being encapsulated inside this constant foo. So this is the enclosing node that kind of holds the reference that we are now calculating. So if you do control space, now this is the moment where the function is invoked and it returns all the elements that are allowed for this reference. And the enclosing node is is the initializer, which is enclosed inside the constant definition. So now here, when we do enclosing node, that's the initializer. And we have to climb up the AST, so we have to ask for the ancestor, and we're looking for the very top root, which is the constants concept. So we're trying to get hold of this guy. So I'll give it some good name, root, whatever. That's the root. And now we take the root, and it has constants. So that's the set of constant definition it has, and that's what we return. So we return only those constants that are encapsulated within our root. So we won't see the constants that are defined in the other constants. So like if you go to your constants, now this flag is underlined, telling you that the reference flag is out of search scope. If you do control space, we only see foo and maximum. So we see only those that are within our scope. So we fixed that. However, we can still refer to foo. Now this doesn't look really valid, does it? So you're right, from the initializer you refer to itself. So we should also restrict that one. So we have to remove something here. We have to remove ourselves from the list. So what we'll do, we'll take the enclosing node, which is again the initializer most likely. We take the ancestor, this time should be constant. So just the constant that we are being used in the initializer of. So now we get the constant, parent constant, that's the one, and we remove it from the list of constants. So we go where it, which is the constant, is different from the parent constant. So we filter the constant so that only those that are different from our parent, only those remain in the list, and that's what we return. So now foo is underlined, reference foo is out of search scope, so we can only refer to maximum in this file. While in this file, when we are, let's say, in the minimum, and we do code completion, we get flag, maximum, name. The current constant is removed. We only see flag, maximum, and name, so the other ones. So that's much better. Now we're almost there. Well, almost. I said almost because we still have to get rid of the forward references like this. This should not be allowed. We can't refer from minimum to name because name is not defined. It's defined later. So we have to remove also those references that are defined later. So this code will be a little bit more involved. So instead of removing us, we now have to iterate and only include those that we find before we reach the parent constant. So basically we have to go integer I from 0 until I is smaller than size of. Okay, we need to get hold of all the constants first, so we go root constants and we store it in all constants. So now we'll go through that. All constant size. So now we get all constants we get the element. So we get a candidate. We get a candidate. We also need well, a list for all the approved ones. So that should be included. So now we have a candidate. Now if the candidate is different from our parent, so the constant that we are defined in, then we simply add it to the approved list of approved constants. Otherwise, if not, if we hit the parent, now we know we are done, so we just return approved. And now if we never hit the R constant, then there's probably some problem. So maybe we could throw an except. Well, you know what? I'll just return. Maybe there's a better way to handle it, but I'll just return all constant in that case. All constants. If we never hit the candidate. Let's rebuild now. Good, so let's see what happens. Now it's underlined, so now it's telling me something wrong. Yeah, so now name is out of search scope. So we are only offered maximum here. While here we are also offered minimum. So now we can't make forward references, we can't make references to ourselves, and and the types are being preserved. Well, the last thing we have to do to make this useful, we need to be able to generate constants. We need to be able to generate Java out of this, which we currently are not able to because the reference has no generator. So the reference is still doesn't know how to generate itself. If you try to generate now, you get a problem here. Text scan not found. That means the generator for some element in your structure is not defined, so it couldn't be generated down into Java. So we have to fix that. So what we'll do, we'll create a generator template for the reference, and so we need to take some reasonable. So we need to take some concept from the base language that we would use as the base. Well, in this case, I would go with local static field of reference. Oops, sorry. Local static field reference. Okay, so that's the one. Well, we don't have any surrounding context, so we can't refer to an existing one, but it doesn't really matter because we wrap it now with reference macro to node original. So now instead of this dummy static field declaration, static field, local static field reference, instead of that we replace it with a reference to the constant, and we use the name of it as a placeholder to put in the code. So let's try how this works. Now going to my constants and generate, And here we go. So minimum is, refers to maximum. Name refers to minimum, just like it does in our DSL. So now we have valid Java generated out of MPS, including all the references. Okay, it was quite a ride, I think. I hope you enjoyed it. That's all for today, and stay tuned for more. Goodbye.